talking about buffers and sort of how buffers work. Remember, again, buffers are really a combination of basically one of two things. It's either a sort of weak acid and the salt of its conjugate base, or you could definitely make a buffer out of a weak base and the salt of its conjugate acid. And remember that really the way a buffer works is they both need to be actually in the solution at the same time. And we're able to do that and sort of keep them both in the solution at the same time because they are weak acids or weak bases. Those weak acids or weak bases, right, will set up an equilibrium. And that will allow really both components, the acid part and the base part, to remain in the solution. You cannot have a buffer that is made up of a strong acid or a strong base, again, because as we talked about, if you had something like hydrochloric acid, when it's in solution, it 100% breaks apart to this part. None of this is there, which means you don't have an acid part in the solution. You have really just the base part. And that's different if you take a buffer like acetic acid. When it's in solution, it will set up that equilibrium. And you will be able to have basically both of these guys in solution at the same time. You'll have, again, sort of the acid part of the buffer and the base part of the buffer still in solution. And you help it out usually because, you add something, for example, like sodium acetate, which is more acetate. So you could kind of build up this part and you'll have a good amount of that part in there. And that's ultimately what gives a buffer really its function to be able to, as we talked about, not be a neutral solution necessarily, but be able to really maintain the pH of that solution wherever it's at. There will be a little bit of adjustment up and down depending on sort of if you add acid or base to it, but you will not see giant swings in pH. It won't go from like a pH of 5 up to like a pH of 12 or 13 or down to like a pH of 1 because it has both of those things in there. And really the reason why it's able to do that is what it does is it pretty much prevents the formation of free H plus or free OH minus in solution that would normally cause a very big jump in pH. So when we're dealing with something that is not a buffer like water, and we throw that hydrochloric acid in, as we talked about, it will produce that H plus and that Cl minus. And really why we do see a really big change in pH is we make a lot of free H plus in that solution. And because pH is minus the log of the H plus concentration, it is the, thank you. It is the amount of free H plus that's in that solution that really affects the pH of it. The more you have, the lower the pH is going to be, and we're going to see that really big swing. And that's the same thing that happens in a non-buffer when you add a strong base. We are generating a lot of OH minus in that solution really quickly. And because the concentration of OH minus is related to the H plus concentration, they really run opposites of each other. So what happens in the base situation is we spike up the amount of OH minus. The resulting is the H plus drops pretty dramatically as a result of that. And we do actually see the pH actually shoot up in that situation when we have a non-buffer situation. Those H pluses, OH minuses really get tied up in the buffer in those reactions. So if we took that acetic acid and sodium acetate buffer, as we talked about, when we add, say, that base to it, for example, it will react with the acid part of the buffer, and we get a double displacement reaction, and we produce a little bit of water here. And what we see, and actually, as we talked about last time, is actually what we don't see being formed when we react it with the buffer is we don't see any free OH minus there on the right-hand side as we did when we put it in water. And thus, if the amount of OH minus basically remains relatively constant, the H plus concentration will also still stay relatively constant. And the result of that is we don't see those really big jumps in pH. The pH will actually remain relatively constant because of that. And the same thing happens when we react, obviously, the HCl. If we reacted the HCl, it would actually react with the base part of the buffer. And the result of that is something like this. And a little bit of sodium chloride. So again, what we don't see on this side in this reaction is we don't see that formation of the free H plus like we do when we put it in water, which is not a buffer. Thus, again, H plus concentration stays pretty constant. The pH remains relatively constant as well. Any questions on that stuff there? The other sort of thing that we also saw in these reactions is, in addition to really preventing that formation of the H plus or OH minus, which is really the thing that keeps the pH relatively constant, is we also will sort of regenerate some of the buffer as a result of these reactions. So as you can see here in the first reaction, we had to use up some of the acid part of the buffer, but the result is we actually made some of the base part of the buffer, which is always what sort of happens in a buffer situation. Since you have an acid part and a base part, you use up one, but you kind of make the other, and it kind of goes like that. Also why a buffer can kind of be sustainable over a good period of time, depending on what you're doing. We also see that down here, we had to use up some of the base part of the buffer, but we did generate some of the acid part of the buffer as a result of it. Any questions on that there? So ultimately, that is what you see. And as we talked about, a lot of times, you might wonder, how can you make a buffer, or how can you sort of choose a buffer to make? Well, a lot of times what we like to do is sort of make a buffer that has sort of equal amounts, if you will. Sometimes that's a good idea to do, of the acid part and the base part of the buffer. And you may be asking, well, how do I know sort of what to make it out of? And we could actually use this and sort of think about making a buffer like this and the Henderson-Hasselbalch equation to help us understand it. Remember, the Henderson-Hasselbalch equation is pretty much the equation we use for buffers in a common ion situation, which is pretty much what buffers are. And that is the pH is equal to pKa plus the log of the base over the acid, where the pKa value, right, is minus the log of the Ka, right? So if we happen in this case to make a buffer with equal amounts of the base part and the acid part, that essentially will turn this into the pH is equal to the pKa plus the log of 1. Log of 1 is equal to 0. Yeah. So when you're trying to decide, what should I make my buffer out of, what you really want to look for is a weak acid or a weak base that has a pKa value, usually about plus or minus 1 of the pH that you're looking to make. So if I was looking to make a buffer with a pH of like 4.6, I would choose something like acetic acid, which has a pKa value of 4.74. That might be a pretty good choice. A really bad choice would be something like ammonium chloride, which has like a pKa value of like 9.25, very, very way away. So when you're trying to choose sort of, what should you make it out of, not all combinations of weak acids and conjugate bases or weak bases and conjugate acids are the same. What you want to look for is, again, one that has a pKa value pretty much near what you're trying to make in terms of the pH of your buffer. Could you make it out of something really far away? You could, but it probably wouldn't be the most effective. It would take a lot of material to kind of get it there. So you do want to kind of choose somebody that has a pKa value of plus or minus 1 of your sort of desired pH. Any questions on that there? So again, as we talked about, when we do add acid to a buffer, what we do see is that generation of more of the acid part, and we use up some of the base part. And as we talked about, when we add some base to it, it will use up some of the acid part and generate some more of the base part of the buffer. So as I think we finished up maybe last time, there is sort of a capacity to a buffer, and there's a couple really important things when you think about making a buffer, which is sort of the goal of the experiment we're starting, which is, you want to make the buffers with a sort of correct concentration, and you want to think about maybe the concentration of the acid or base that you may be adding to it. Again, if we were to just continuously add acid, or kind of grab an acid that is way too strong for our buffer, what we will essentially continue to do is eat up the base part. And at some point, it will no longer be able to function as a buffer. And as you continue to add acid at that point, now you're going to really see a pretty good jump in the pH, because you're just adding a bunch of H plus to that solution, and you will see a good jump. So, there is a limit to the buffer, how effective it is. And again, you want to think about sort of concentration and how much you're adding of acid or base to it. Any questions on any of that stuff there? Okay. So let's get into maybe some calculations here. So why don't we start with just A, you do A, and then we'll talk about it, and then we'll get into B. So for A, we want to calculate the pH of a buffer system that contains 1 molar acetic acid and 1 molar sodium acetate. The Ka value for acetic acid there is on the bottom. Okay, let's take a look at A here. So we're looking for a calculation of this buffer that contains 1 molar acetic acid and 1 molar sodium acetate, with the Ka value given there. So it was nice enough to say it's a buffer, but again, if for some reason it didn't, you hopefully should recognize that these two things are basically related to each other. And again, we know for sure that is a weak acid because we have a Ka value. And again, this is the salt of its conjugate base. The conjugate base really is the acetate part. The salt really just because there's a sodium there to balance out the charge. Sodium is really just a spectator ion, not really doing much, but hanging out there. So we do have a weak acid and a conjugate base. So that should definitely point in the direction of a buffer. Because of that, we can go right into the Henderson-Hasselbalch equation, and we could calculate the pKa value there by taking minus the log of the Ka, which would be minus the log of 1.8 times 10 to the minus 5, gives you like a 474. At this point, we could go right in and do pH is equal to 4.74 plus the log of the base, which would be this guy, and it is 1 divided by our acid, which would be 1, just like a second ago. That is going to zero out basically, and we will end up with a pH of 4.74 in this case. Any questions on that there? Now, again, if you did not want to use the Henderson-Hasselbalch equation, as we talked about, you absolutely could still do ice tables if you're more comfortable maybe doing an ice table. The ice table will be based off of the weak acid. So you would just set up your weak acid. And when you do your ice table, you would have 1 here. This would be 0. And most importantly, when we talked about sort of doing common ions and really buffers with an ice table, this is the spot that is commonly messed up by people on this side. We actually do have an initial concentration of acetate. It is coming from the sodium acetate up here. So you do need a 1 here to do that side. The change here would be minus x plus x, and at equilibrium 1 minus x, x and 1 plus x, not minus x there. That obviously would go into your Ka expression like we've done before. You would solve for x, you could make an assumption, all that good stuff. And at the end, you should get the H plus concentration, which should lead you back to this pH as well. So again, you could always 100% do an ice table. Again, I just caution you in this situation, very, very common mistake is zeroing out that size. So you got to make sure that you don't do that. Otherwise, again, you're basically just doing the weak acid problem over. Any questions on either of that there? Okay, so let's take a look then at B and what happens in B. So when we look at part B, we're going to take this same buffer and we're actually going to add some HCl to it. In the sake of this calculation, we're going to assume that everybody is just 1 liter just to keep the volume constant. That is not always the case, so you do have to take into account the volume usually, but just to keep it for this first calculation here, everybody we're just going to assume is basically 1 liter. Now, when we add volume to volume, does the molarity stay the same or does it change? So if I have a beaker of a buffer there, and I add some acid to it, which is more volume, does the molarity of the buffer and everybody, do they stay the same or do they change? It does change, right? Molarity is moles of solute technically over liters of solution. So when we add a solution to another solution, what we are essentially doing is increasing this number, right? Which means the molarity is actually changing. So in buffers, which it commonly happens in this situation, and later as we'll talk about with titrations, which you are constantly doing nothing but adding more volume along the way, the molarity always is changing, which means we do not want to do our calculations, especially our ice table calculations of molarity, because it is constantly changing. So typically in a situation when we're adding volume and we need to do an ice table, which is what we need to do here for part B, is we want to do that in moles. So we typically want to do the ice table in moles. Moles remains constant because however many moles you have in each of those, they remain. There's only so much moles that you put in there. And that's really what's reacting, by the way, right? When we put two things together, it's really the solute, right? The moles of the solute that's in the solution is really the thing that's reacting. So when we add acid or base to a buffer, you need to do an ice table to figure out what's happening to the buffer. But you do need to do it in moles. And again, like I said, we will see this again with titrations where we're constantly adding volume. So the rule is essentially you do the ice table in moles, and then what you want to do afterwards is actually convert it back to molarity at the end of the ice table. So that's really the right thing to do. We would convert it back to molarity at the end by dividing by the total volume. So in the case of this, the volume of acid we added, right? And the volume of the buffer, we would add that together and divide it out at the end. And that would convert our moles at the end of the ice table back into liters. Obviously, we need to convert it back into moles. We obviously need to convert it into liters, obviously, before we divide it back. So those are sort of the rules when we're adding volume to something. Ice table in moles, then convert it back to molarity at the end when you get to your equilibrium line by dividing by the total volume in liters. And then you should be good for whatever calculation you got up at the end of the ice table. Any questions on that? So again, this one's a little bit different since we're just going to assume everything's 1 liter, but normally you would have like, you added 20 mils of acid to 40 mils of buffer. Your total volume obviously would be 60 milliliters. So you would keep track of, the volume. So let's take a look at this. We're going to, in this case, add 0.1 molar hydrochloric acid to this buffer. So we have our same buffer. We have our 1 molar acetic acid. We have our 1 molar sodium acetate. And we're going to add 0.1 molar HCl we're going to just assume, again, for this particular problem, not always this case, obviously, that everyone is basically 1 liter. So everyone is 1 liter. We are obviously using the same Ka value that we had before, the 1.8 times 10 to the minus 5. All right, so we do need to do an ice table here. And the purpose of the ice table is really to figure out what effect the addition of this acid is going to have on really the buffer, right? So first off, we need an equation. Actually, before we start that, I will do the equation first. So when I add the HCl to this buffer, is it going to react with the acetic acid or the sodium acetate? It should react with the sodium acetate, right? Because that's really the base part of the buffer. So we're going to get a reaction between these two. And again, it's going to be a double displacement. We're going to produce the other part of the buffer, which is acetic acid, and we'll produce some sodium chloride as well. Any questions on the reaction there? Okay. So we do want to do an ice table here. And again, we do want to do this ice table in moles. So initially, we're going to calculate the moles, which in this case, since we kept everything as 1 liter, I'll just do 1. You take 1 liter times 0.1 moles per liter, gives me 0.1 moles of HCl, right? Basically, it's going to be the same number in this case because we're keeping everybody at 1 liter. So we are starting here with 0.1 moles of our HCl. Now our sodium acetate, we have 1 liter, that is 1 molar. So again, 1 times 1 gives us 1 mole of our sodium acetate. Do we have some acetic acid there? We do, right? And this is also, again, a very common mistake. If we don't put anybody over there, this is not a buffer. So we do have some acetic acid. It also is 1 molar times 1 liter gives us 1 mole of acetic acid. And we could zero out the sodium chloride if you like. First off, any question? Yeah. We're adding 1.1 molar of hydrochloric acid, and we're going to assume that we're using a liter of it. So 1 liter times the 0.1 gives us that. Yeah. And again, like I said, just in this particular one, we're just assuming 1 liter, but normally, like I said, it'll say like you added 5 milliliters of the HCl. So you would do obviously 0.005 times the HCl and so forth. All right. Now, if this is a buffer, which it is, and if we assume, like you probably can in most book problems, that this buffer should function correctly, what should happen to the HCl when I toss it in there? Should it still be there when it's all done, or should it be gone? What should happen? When I toss the HCl in there, it should react with the sodium acetate, and really the buffer should kind of take care of it, right? So as we talked about, it won't allow it to really kind of break apart and be free. It's going to tie it up. So in this table, we actually know the change. We're not going to use X's in this case. We're actually going to use what should happen, which is when we add this HCl to it, it should actually use up all the HCl, which means the change here will actually be minus 0.1 moles. So we're actually going to use a number. And that is very common when you do an ice table in moles. Instead of using X's, you use like numbers. So in this case, the HCl is like the limiting reagent. This will also be minus 0.1 moles. This would be plus 0.1 moles on that side. It is like the limiting reagent because, frankly, if you look at this number here versus this number here, the one that is bigger is the guy on the right there, yes? And that means you have plenty of moles to take care of what you just added there. All right. So again, the HCl here is the limiting reagent. When we get to our equilibrium, that's going to zero out our HCl, which we would hope, because we hopefully made up a good buffer. We will end up with 0.9 moles of this guy, and we will end up with 1.1 moles of this guy here. Now, let me ask you, why am I not writing really anything in this side? Because what we have there is sodium chloride, right? And sodium chloride is what type of salt? It does come from strong, right? So that means it's relatively weak, which means it's a neutral salt, right? So it's not going to affect the pH. Again, great idea in nice tables not to put numbers near anything that you should not be using anyways, right? So because it's not going to affect the pH, we don't need to put any numbers, so you don't try to use it incorrectly along the way. So that's really why I ignored it. First off, any questions on this ice table here? Again, needs to be done in moles because we're adding volume, which means molarity changes. And typically speaking, when you're doing one in moles, really no X's, we will use real numbers, and it should be the smallest number on the guy on the left. We know it should be the smallest number of the guy on the left because if we use the larger number, what would happen to our number on the left there? If I subtracted 1 from everybody, I would end up with a negative number, right? You can't have negative numbers, so that's a good thing just to keep in mind. Common sense there, don't have negative numbers for concentrations or anything like that, or moles. All right, at this point, when I tell you this, trust me, it's really good practice at this point to now convert these guys back into molarity. So you want to do the ice table here in moles, you want to get it to the equilibrium line, you want to definitely convert it back to molarity. So again, in this case, we're just going to assume everybody's still just a total of 1 liter, and that's not normally the case. So you would have to again add up the total volume, which would be how much acid you added to how much buffer you started with. So we'll just divide everybody here by 1 liter, which will turn this into 0.9 molar and 1.1 molar. Very, very good practice to make sure you do that. It will put you in sort of the right position for pretty much most calculations that you might have to do at this point. So ultimately, though, we're looking for the pH, right? So if you were not sure what is going on at this point, you can still look at your ice table. And at this point, it should also help you. We could see clearly from our ice table, we have this guy left over and we have this guy left over. And hopefully you can still recognize that as a weak acid in its conjugate base, which means this guy is still a buffer at this point, because hopefully we made a good buffer, right? Which means if I want to calculate the pH of the buffer, what can I use at this point? I can at this point go right into the Henderson-Hasselbalch equation. So we can go into the Henderson-Hasselbalch equation at this point. You could also lay up a ice table if you preferred. The pKa value is still going to be the same. So the log of the base, so we want to make sure we get the base, which is actually over here. So that is 0.9. And our acid is 1.1. So 0.9 divided by 1.1, a little log action, plus a 4.74. Calculator almost dies. I think 4.65, I'm hoping in this case. First off, any question on that calculation there? Now, a couple of things that we want to make sure, well, does our answer make sense? Well, it should move, right? Because even though it's a buffer, it will move a little bit up and down. Since we added acid, we would expect the pH to go which way, up or down? Down, and it did, right? It started at 4.74, and after we added the acid, it dropped to 4.65, which is still the same ballpark, and it went in the correct direction. Now, if you did some type of calculation and you find yourself with like a pH of like 4.9, you're definitely going in the wrong direction. Yes. So these are things you want to kind of think about to make sure that your answer makes sense. You maybe didn't inverse a couple of numbers along the way when you did it. Any questions on any part of that? Yeah. How you would do the ice table on this one? Yeah. So let me Go here, go here. So, so I believe at the end of the equilibrium line, right, we had basically 0.9 molar of the sodium acetate, I believe, right? And we had 1.1 molar of the acetic acid. So if you chose to do the ice table, you again would set up the equilibrium with the acetic acid in this case. And you would use these equilibrium values as your initial values in the ice table. So this would be like 1.1, this would be 0, this would be 0.9. And then obviously this, you would use X's on this table. This would go into your Ka expression. You would solve for X. And then obviously the X would be the H plus concentration, which would then get you to the pH at that point. Yeah. And again, you should end up with pretty much the same answer, maybe slightly different if you did a little bit of rounding along the way, but you should be pretty close to that, whatever we had there, 4.65 number. So basically after that first ice table, after you convert it back to molarity, you would just take those guys as your initials in the sort of ice table for the acid there. And again, the importance of that is you got to make sure you got that number on that side. Otherwise, again, it's not going to be a buffer. Other questions on that? Okay, one other thing here about this. I personally think you should always convert back to molarity, and you should. But I will tell you the honest truth is if you choose to do the Henderson-Hasselbalch equation, not the ice table, but the Henderson-Hasselbalch equation, you can actually go into here with moles. So it will work out the same. So if you use the moles there, it will work out the same. And it does that because you're dividing, so the volumes cancel each other out. But if you go into an ice table, you need molarity. And there's several other calculations that we'll do along the way when we get into titrations that you need molarity afterwards. So it's just the safest move to do, even if in the buffer situation, you technically could use moles. It is the safest thing to do is to convert it back to molarity because it will again set you up for success for the rest of the different type of calculations that we'll do along the way. But technically speaking, you definitely actually go in moles if you go into the Henderson-Hasselbalch equation. Question on either of those calculations. So earlier we talked about as well that there is a limit to say buffer capacity. So let's take this buffer here before we move on to another example and talk about what would happen if maybe we grabbed the wrong thing off the shelf or we didn't make a buffer that was correct. I know that would never happen, but So we'll go with our same 1 molar acetic acid buffer here. And we'll use our 1 molar sodium acetate buffer. And again, we'll say we have just 1 liter of it. And let's just say instead of grabbing the 0.1 molar hydrochloric acid, you find laying out there for some odd reason, like the 18 molar hydrochloric acid. And you think that's a great idea. Let me add a liter of that to that solution. All right, before you pass out from the fumes of opening that bottle, you will do this here. Hopefully you did it in fume hood, I hope. So we're going to get a similar reaction. We're obviously going to get our HCl in this case is going to react with our sodium acetate. And we will get our acetic acid, just like we had before there, and our sodium chloride there. Now, if we do our ice table like we did before, we're going to do it in moles. So we would technically have 18 moles of this guy. We will then have 1 mole of this guy and 1 mole of this guy. Now, when I add that acid to this buffer and I look at my ice table, what's going to actually get used up on the left-hand side? I can't have a negative number, right? So in this case, this now becomes the limiting reagent, right? This is like your excess reagent. So the best that this buffer could do is handle like 1 mole of that 18 moles, which means at that point it's done. So the change is actually going to be, in this case, the sodium acetate, which would be -1, -1, and plus 1 here, which means when you get to equilibrium, you got 17 moles of this guy, you got none of that guy, and you got about 2 moles of this guy, which obviously you can convert back to molarity if you wanted to. But now let's take a look at our ice table and see what we have left. We have this guy left, and we have this guy. Is that a buffer at this point? That is not a buffer at this point because HCl is not related to acetic acid. We actually now have basically 2 acids rolling in that beaker. We got the acetic acid, which is the weak acid, which is going to generate some H+. But more importantly, we have this guy, which is a strong acid, which is 100% going to generate a lot of H+. Would we expect the pH to jump in this case? We would expect the pH to jump very, very big. Yes, and it will actually jump pretty down to like 0-ish probably in this case, because basically we blew right through the buffer. There's really no base part of the buffer. We blew right through it. And at this point, we're just dumping in H+ that solution. We will see a really, really big jump in pH. So this is what we're talking about. It's sort of an extreme example here, but this is sort of the capacity that buffers have and why you have to think about not only what you're adding to it, what the concentration of your buffer is really important to make sure that you really do have sort of a functioning buffer that will not really be kind of blown right through depending on what you're adding. That's why it's important to also read labels when you do experiments like this, that you don't grab the wrong molarity because you will blow through perhaps your buffer. Any questions on that? And this is also what I was talking about earlier. When we talk about things reacting, it really is how many moles of those solutes you have floating around that solution that's there to react. And, once they're gone, we can't react anymore. All right, so why don't you try one now? Calculate the pH of a 0.3 molar ammonia and 0.36 molar ammonium chloride buffer system. What is the pH after you would add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer? So in this problem, we're not keeping anybody constant in terms of volume. So you got to take into account the volumes of each of those things. By the way, the buffer is 80 mils, has both of those things in it. Yeah. So when it says 80 mils of the buffer, that's 80 mils of the NH3, NH4+. That's what's happening there. Let me give you probably a Ka value would probably be helpful, I imagine, maybe. What would be that Ka value? That is this, I think. Let's go with Ka value for NH4 plus is 5.6 times 10 to the minus 10. All right, you're looking for 2 answers. We're looking for what is the pH of the buffer solution before you add anything to it. Then we're looking what is the pH after you add sodium hydroxide. So take some minutes here, see what you come up with. Okay. All right, let's take a look and see how we're doing here. So obviously it's a buffer. It was, again, nice enough to tell us it's a buffer, but sometimes they don't tell you it's a buffer. So what we want to look at is, what we got going on here. We do have NH3, which is a weak base. And we have NH4 plus, which is really its conjugate acid. So to be honest with you, in this problem, maybe they give you the Ka value, maybe they don't. Maybe they give you the Kb value, maybe they don't. Maybe you have to go to a table, and the only one you can find is maybe the Kb value, which is 1.8 times 10 to the minus 5, and that would be for NH3. So there's a couple of different things that they may give you or may not give you in a problem like this, and then, you could use some of it whichever way you want. So we'll first go with the Ka, since that's what I gave you for the NH4 plus. And really, because it's a buffer, you don't really need to do an ice table. We haven't added anything to it at this point, so we could just use the molarity of the actual buffer components to figure it out and use the Henderson-Hasselbalch equation. Again, if you wanted to do an ice table, you could either do the NH4 plus as like an acid and use the Ka value, or you could use the NH3 as a base and use the Kb value and then convert to pH afterwards. So you could do it either way like that. But here we will turn our pKa value here minus the log of the Ka, which is minus the log of 5.6 times 10 to the minus 10. That gives us a 9.25, I believe. Now we could go right into the Henderson-Hasselbalch again because it is a buffer. So that would be 9.25 plus the log of the base, which in this case is the NH3. It is the base, has one less hydrogen, right? And the NH4 plus has the extra hydrogen. So we want to actually go 0.3 over 0.36 in this case. And that will get us like a 9.17 as our opening pH. Now, when we look at it, this is a acidic basic buffer. This is a basic buffer right at a 9.17. So while we're here and looking at this part, before we go to the second part, as I mentioned, maybe you only have a Kb table available to you, or you're given just the Kb value. So you could turn that into your pKb by doing the same calculation, which would be minus the log of our Kb value. And that would be 1.8 times 10 to the minus 5 is our Kb value. So we would want to take minus the log of that. So minus the log of 1.8 times 10 to the minus 5 gets you a 4.74 for your pKb value. Now, if you wanted to, you could have done that other Henderson-Hasselbalch equation that uses the POH, right? And you could have done the POH equals the pKb plus the log of the acid over the base. And that will get you a 4.74 plus the log. Now we want to make sure we do the acid up on top, 0.36, 0.3. And that would get us 0.36 divided by 0.3, take a log of it, plus 4.74, gives us like a like a 4.82 on some rounding there. You want to remember, though, that that is not your pH in this case, right? That is your POH. And you would then have to obviously subtract the 14 in this case. And it gets you a 9, not a 19, a 9.18. So you can see you get a slight difference in that last number just on some rounding of the Kb and Ka type values, but it basically gives you the same number. Alternative to that is you could have got your pKb value here and did the pKa is equal to 14 minus the pKb. And that would obviously get you your 14 minus 4.74. And again, you can see you have that slight difference in that last digit there. And you could have then took that up to here, obviously, and just went into there as well. So there's a few different ways you could have approached it. They all essentially give you basically the same answer, just a slight last digit with rounding. Yeah. If you were just had the Kb value, absolutely, that would be another way. You could have used Kw, get the Ka, and then turn it into the pKa. But again, that relationship of the, which is what I did right here, which is the pKa plus the pKb equals 14, might also be a little bit quicker just to do it that way, and it gets you kind of the same points as you want a pKa value. But you absolutely could use Kw to get to the Ka and then get the pK that way. Yeah. It is, yes. Yeah. Any questions on any of those ways? Again, what this shows you is a couple of things. Like I said, sometimes people will use that POH version of it in a basic situation. But again, in my personal opinion, you still got to do all that work anyway. So why not just stick it into the Henderson-Hasselbalch and just get the pH is what you want anyways at the beginning, but not wrong, obviously, to do it that way. And there's a couple different ways you can always get there. Any questions on the first part here? All right. Now let's talk about the second part here. We're going to, in this case, actually add some sodium hydroxide to this buffer. And we'll come here. So that's 0.3 and 0.36. Just to rewrite this stuff here. So 0.3 molar NH3, 0.36 molar NH4Cl. Was it 0.05 molar sodium hydroxide, which has a concentration of 0. What was that there? That was the concentration. We're adding 20 mils of it. Yep. So we're going to add 20 mils of this guy to 80 mils of that guy. I think we got everything we need. I hope. Yeah. Okay. So just visually what we're doing here is we got our beaker over here that is 80 mils and it has the buffer in it. And again, our buffers are same basic components. It really is the NH3 that's in there and the NH4 plus is the buffer. The Cl minus is really just a spectator ion, and that's what makes it sort of the salt. And we're going to take the 20 mils of our sodium hydroxide, obviously, and drop it in there. We obviously could get one information from that right there that's important for us, which is the total volume at the end, right, is going to be the 80 and the 20, which means our total volume at the very end would be 80 mils plus 20, gives us 100 milliliters total volume. All right, so obviously here we're going to need to do an ice table, and really the purpose of this ice table is to figure out what happens to the buffer when we add the sodium hydroxide. Should I do that ice table in molarity or moles? Again, we should do it in moles because we're adding volume, so our molarity will change. So we'll start with maybe calculating the moles of everybody. Let's do the moles of NH3. So the volume of the buffer, yeah, sure. You can, again, you just get millimoles, so it will work out as long as at the end you divide by milliliters. So if you take milliliters times molarity, you technically don't get moles, you get what is known as millimoles, which then if you go back and divide by milliliters, it becomes molarity again because the milli and milli cancel. So I would recommend maybe doing liters to moles, but technically you can as long as you remember to kind of divide by the milliliters at the end. And remember that the number that you get is actually not the moles. So, because if you use that as the moles, you'll be off by a factor of 1,000. Yeah. Okay, so we're going to take our 80 milliliters, convert it to liters here. And we're going to times it by the molarity of the NH3 part, which is 0.3 moles per liter. Liter is going to cancel, going to get us for our NH3 0.024 moles. We're going to do the exact same thing basically for our NH4 plus, 0.08 liters times the 0.36 moles per liter. Again, liter is going to cancel there and going to get us 0.08 times 0.36, 0.0288 moles of NH4 plus. So I went way high on that. There we go. Now, again, a reminder, the reason we're using 80 milliliters for both parts of the buffer is they are both in the same beaker to begin with. So that is the total volume of both parts of the buffer. So that sometimes confuses people, like, is it for both, or do we need to go 80 and 80 or something like that? But when you get a number like that, that is basically just the total volume for the buffer part. So you would use it for both of them. Our sodium hydroxide, we got 20. So we'll do that guy there, moles of NaOH. 0.02 liters times our molarity of 0.05 moles per liter, going to get us 0.02 times 0.05, 0.0010 moles of sodium hydroxide. All right, any questions on any of those numbers there? Okay, now that we got the moles of everybody, we're ready to do our reaction. When I add the sodium hydroxide to our buffer, it's going to react with which part? Yeah, it is going to react with NH4Cl. Again, when you look at this buffer, this is really the base part of the buffer, right? And this guy is really the acid part of the buffer. Since I gave you the Ka for that guy, you can think of it as the acid, obviously, as well. So that is going to be the reaction that we're going to get. So we're going to get our sodium hydroxide here is going to react with our ammonium. I'll leave the whole thing chloride in case you're curious. You're then going to get a lot of things formed in this particular case, but you are going to get NH3 formed. You will also get some water, and you'll also get a little sodium chloride action going on there. The last two really not important for our calculation here, right? The NH3 is really the important part of it. Any questions on that? Obviously, if you took out the Cl, you would end up with NH3, water, and some sodium floating around by itself, right? As well. And again, sodium wouldn't affect anything as well if you kind of left it out. So we're going to do our ice table here. And we're going to use our moles there. So we got 0.001, if I didn't add an extra zero, 0.001. For our NH4 plus, we got 0.0288, 0.0288 moles. And again, really important here, we do have some NH3 there to begin with, which in this case is 0.024, looks like. 0.024 moles. Again, this is water, not going to really affect anything. And again, the sodium chloride, not going to really affect anything. Might as well just leave them blank. Any questions on the opening table there? Change in this case should be the moles of the sodium hydroxide, right? So the buffer should take care of that. Again, just simply thinking about it like math, that is the smaller number. So that is going to be the change part. You won't run into trouble if you always remember, go with the smaller number. And remember also on this side, we are plussing it on that side there. That is then going to zero out our sodium hydroxide like we hoped for. We will end up with 0.0288 minus 0.001. Gives us a 0.0278 moles for this guy. And 0.024, remember we're plussing in that side, 0.001 gives us a 0.0025 moles at this point. Any questions up to there? Now, like we talked about, technically speaking, you could leave it in moles, but we're going to convert it back to molarity so we don't run into trouble later on in our life. We already calculated earlier, right, that our total volume was 100 milliliters. So we would want to divide each of these by 0.1 liters, right, which is obviously 100 milliliters converted into liters. Yeah. Maybe I add an extra zero. I think you're right. I just saw it on my calculator. Thank you. Had it on the calculator. Look, I failed chemistry 3 times. It's all right. I was a history major. 0, 2, 5. There we go. Thank you. All right, now we got the right now zeros there. So 0.0278 divided by 0.1. We're just going to move it over there. 0.278 molar and 0.25 molar here. All right, at this point, if you weren't sure, you can again look at the ice table, and we do see we have this guy and really this guy left over. And again, we hopefully should still recognize that as a buffer, which we would hope in this problem. So once again, to get the pH, probably the simplest way would be to just go right into the Henderson-Hasselbalch equation at this point. And again, whichever way you want to do that, I'm going to just use that 9.25 as my pKa value like we did previous, plus the log of our base, which again is the NH3, which is this guy, divided by our acid, which is this guy. And we will end up with here 0.25 divided by 0.278, a little log action here, plus a 925. Looks like a 9.20 on our pH at this point. Any questions on that? Yeah. You're good? Okay. Other questions? Again, we could think about just logically what is happening here, which is things we want to think about. When I add the sodium hydroxide to that buffer, would I expect the pH to go up or down? It should go up. And we started at like 9.17. We added a little bit of base and it went up to a whopping 9.2, which at least went in the correct direction, right? So it went up, it didn't go down. So again, these are things you really do want to kind of think about when you get your answers at the end. You know, does it sort of make sense? There's a lot of places where, again, people kind of inverse numbers and reverse numbers and stuff like that. So you want to make sure you kind of, at least things sort of make sense. Any questions on any of that there? Questions on buffers, how they work, how to calculate them? Buffer professionals now. I like it. Okay, so we'll lay up the lecture here for now.